Hello, and welcome back to my 486 project. And it's been a little bit of time. The short version is that I've been working with hardware designs and trying to solve the problems related to it. So, not going to be a lot of building this particular episode. It's all going to be about technical discussion, so feel free to skip it if you're not that interested. Okay, to start with. This is sort of the first rough idea I had for the design of the board. And there's a lot to this. There's a lot of pins. There's well over 100 pins that are necessary for the fully functional 486 bus. And I do want to have it fully functional, which means the ability to switch between 8, 16, and 32-bit data buses, and all the various other features. About the only thing I'm really not looking to implement at the moment is the external cache logic. So the problem is that this is a fairly big board. This is 100 by 200 millimeters. To compare, this is just a blank of the CPU board. You can see that how that fits. This is 100 by 100. And my first plan was to have this be like a flat backplane and have the boards sort of spaced out on it. But if you look at this, it's a lot. I mean, if I have like just a couple boards here, you can see it's already exceeding the size of the camera space. It's just big, and it's big with stuff that is going to be mostly irrelevant in the long term. There's a lot going on and not a lot happening. And there's also the problem that if you look at this, making a generic backplane or stripboard for this is a pain, because a stripboard doesn't work. We have too many pins that are lined up. We have the pins on the side, though most of these are optional and can generally be ignored. They're there for completeness. But yeah, there's a lot of pins, and any backplane I make for this particular design would have to be completely custom. Either I have to wire wrap it, I have to make it myself, I have to actually get it manufactured. It's a big project, and it's not what I want to do for a simple backplane. I mean, the whole point of a simple backplane is that it should be simple. So my next thought was to have this use an edge connector. There's a lot of different standard edge connector styles that I could look into. We have the standard there's the standard AT connection that the 2A6 used. That has some problems in that it only has 24 address lines and 16-bit data lines. And once again, I want a full 32-bit by 32-bit bus. So that was not workable. Next would be PCI. Now PCI is designed for 32 bits. So it has both a 32-bit address bus and a 32-bit data bus. The problem is that they're all multiplexed together, meaning that I'd have to have logic to latch and shift data around between the various pins on every card. And that is a lot of overhead I don't want to have to do. And that leaves PCI Express. PCI Express has enough pins, but I'd have to completely abandon PCI Express as a connector. I'd just be using the physical connection, but none of the electrical components. Not the worst thing in the world, but it still has issues. The biggest one is that the sockets, the slots for this, because they're edge connectors, is a little expensive. Not as expensive as some of the other ones. Some of those can run easily into the tens of dollars each. So, sometimes some ATX stuff was running like $70 a slot. It's like, I can't afford that. I could, but it's not much. It's exceeding the budget I have for this project. Let's put it that way. So I'm left with a bit of a mess. I mean, I could use the PCI Express, using the widest form of that, like you would see on video cards. And I did do some preliminary design work on that. But I end up in the same problem with the backplane, is that I still have to custom manufacture a backplane to use that. What I really want is a connection system that is reasonably standard, enough that I can buy components and a generic backplane for, or something that I can easily make into a generic backplane. And that's where I came to this. This, rather a bit of a mouthful of an IEEE spec, is usually referred to as Euroboard or Eurocard. Now, this spec is nice in that it is purely a mechanical specification. It specifies the shape and size of the various boards, how everything is arranged and laid out on them, how the shape of the connector is, and how the connector is built. These are all standardized systems, standardized components, standardized sizes. Now, this does have some benefits, particularly since this is a purely mechanical specification. It's designed to be built on. So while it does specify a connector, the connector having 3 rows of 32 pins, which has some optional configurations, I'll get into that, it doesn't specify any electrical capability, so I can use whatever I want. So doing that, using this particular specification, I get this design, which is slightly bigger than the previous one, where the previous design was 100 by 200. This is 100 by 233.35, and it might be hard to see with the camera, but I've gone through and done a lot of measurement details on this to make sure this fits the actual Eurocard specification. So, what this does get me is there are standard connectors, which are actually reasonably cheap. I say reasonably. They're like $8 per connector or something, but that's not the most expensive thing in the world. And secondly, it solves my issues with pins, because, let's see, which one is the 3 by? Yeah, okay. Let's see if I can actually get this angle so you can see it on camera. This particular connector has 3 rows of pins, which is nice and standard, and gives me all 96 pins that the connector offers. This version has 64 pins. Can I get that good view on the camera? There. Now, this is nice in that, it's just using the inner and the outer connectors. This is A and C, where this is A, B, C. This is A and C. But this is a connector that is universal, so I can connect this 64-pin one to the socket for 96 pins, and everything works. They're not separated out like that. So I can actually use this to my advantage. Now, the best way to use this to my advantage is by taking advantage of, the strip boards, because this is a very standard design, so it means there are standard strip boards for this. Now, these are bus boards, the same, bus board company. And these are just 3U because it's a rack-mounted system, so 3U is the height, 3 units. And yeah, they're designed for this specific use. Each of the round pins are connected to each other round pin along the line, and the square pins are connected to each of the square pins along the line. Meaning, I just have to solder in a socket to this, or multiple sockets, and I have my backplane. It's not perfect. It's a very generic backplane that has that does nothing but just push data around, but it solves my problem. And the upshot of this is, I say upshot. A complication, but one that's actually a beneficial one to me, is that if you notice with this design, there are only 2 sets of connected pins. They're paired, but there's only 2. And that's because this particular board is designed to work with the 64-pin connector. But this is not a problem, actually, because if I go to, this is the layout of the data bus. This is a little bit more accurate here. This row here is this connector, both A and C, and this row here is this connector, both A and C. And the best part is, I can fit everything I need on just these 2 sets of 64 pins, which includes 4 power connectors, 2 on each connector, 8 ground connectors, which hopefully is going to be enough, as well as all the address lines, the data lines, the control bus, the data bus, the various system managements, the byte, the ability to put the hold, the reset lines, and the interrupt request lines, which is a future part of the project, but I want them on this bus. And then I can use the intersets of pins for some of the more advanced CPU-only features. Stuff like, the parity, data parity, which I'm not planning to use, but some DRAMs have data parity built in, and if I ever implement a DRAM on this, it'd be nice to have that available. The more advanced cache functions, and then the rest is just unconnected, as well as all the extra pins from the future models of the DX. Now, I have these on here mostly because it's good to have them exposed, but partly because I do intend to eventually upgrade the system from the DX25 that I'm currently using to a DX233, which is the one it's double clocked internally, so it'll give me a 66 megahertz processor. And that is my design goal for the hardware. I want to make sure everything I'm building can run at 33 megahertz. And that adds a few extra pins that I need to worry about, so that's part of why I have them exposed. But it does mean that for this initial backplane, only caring about these pins is fine. It works, it covers everything I need, and I can build on it. Now, eventually, I do want to put in a full custom backplane. Now, one of the things, I keep bringing papers in, one of the ideas I had when I was working with this, when I was going through the idea of using standard edge connectors, was that, well, if I was going to do that, I should make it an ATX motherboard, or ATX compatible. And that's what this is. This is scaled down, so this is a different scale, because ATX motherboards are actually bigger than a standard US letter page. But this is roughly what it would look like. We'd have 6 slots in the standard backplane configuration for Eurocard, with the mounting brackets for ATX, as well as the ability to connect the ATX style power supply and the pins from the front of the case, which includes power, reset, the light, and the various LEDs. Now, I always intended to use an ATX power supply. They're just simple, they're convenient, they work much better than what I have. That's one of the problems with this board, is that this little power supply doesn't really have the amperage necessary to drive what I'm looking for. Instead, the ATX power supply, which this is an ATX Nano, does have all the various voltages and has more amps than this does, that you can't see. Now, this is important because I said I always intended to use an ATX power connector for this. And to that end, I do have a breakout board for it, so I can actually use it on the breadboard. So it just plugs in right there. Give it a nice firm click. There we are. And that's in. That is just a straight ATX power supply. Now, this does have a nice clunky power switch, though. But while that is a workable power switch, it's not what I need in this scenario. Because I said, one of the goals is to have this hook be mounted in the case and use the case buttons. And the power switch on an ATX case is a soft power switch, in that you press it to turn it on, you press it to turn it off. All it does is just connect a circuit, and there's logic on the board to handle that, as well as the ability to hold it long enough to turn it off, to force power it off. So I would need to build that logic. Now, that logic is pretty straightforward. It's just a couple of, I believe, flip-flops can make it work. It's been a while since I looked at the design. I apologize. The problem is that power, on a CPU or power supply has a few more requirements than that. It has specific timing requirements. It has specific voltage requirements. There's overvoltage requirements. And while I can probably get away with ignoring all of them, I'd rather not, and I'd rather know what I have will work. Now, it turns out that this is a very common problem. So common, in fact, that there's a chip for it. Now this chip, which is just the, where's the actual number on here? Oh, there it is. I do not know why I missed that. Yeah, a Max 16054. Now this is a nice standard chip. It provides exactly what you want. It'll give you the soft power switch. It lets you externally clear it. It has both high and low outputs to indicate the current state, so you can pretty much hook it to any logic. It is really simple. It does have one fundamental problem, though, and this is where things become a bit tricky. That problem is that it is a very, 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 very tiny chip. Let me put that over. All right, let's zoom this in so you can actually see this, because this is tiny. Focus, please. So, let's get the light adjusted there. I apologize for the shakiness of it. So, yeah, there's my finger. That's tiny. That is very tiny. Now, it's a standard package. It is, God, I can never remember the exact name of this. An SOT 23-6, which I think is because it's like 2 millimeters by 3 millimeters. Now, I've worked with this size of package before when I did the, remember my little triggers here that I misnamed? So I know I can solder them to a point. I'm just going to zoom back out again because this is a little too small. So I know I can work with them, but it's not easy. And when I say it's not easy, I bought 5 of these chips. This one is the only survivor. So I want to emphasize that. It survived. All the others were destroyed in the process because my soldering station isn't very good. It is sort of a midline, no-name brand system that, while it does have some temperature control, it's not the greatest. And it's a very, very fat tip. And because it's a no-name, middle-of-the-line product, I can't get a replacement tip that's a fine enough pitch to work with this in a way that doesn't cause bridges or damage or whatever. So my solution was instead get somebody else to make it for me. Okay, I guess I should probably zoom back in again. So this little darling is just a simple chip. You know, it's overly fancy because it really is just a breakout board. But I got this made from JCB PCB. I hope I got that right. And it actually wasn't that expensive. The chip itself is like $1 per, so $5 for the chip. The board to make 5 boards was $2. And the manufacturing and shipping added only a little bit more. So in total, I was able to get 20 of these manufactured boards for only about, did I say 20? 5 of these boards for $20. Good Lord, did I actually screw that up? I'll have to check the edit to see if I actually said that backwards, because I think I did. But yeah, so I was able to get 5 of these manufactured for 20 some odd dollars, which includes shipping. And it's really straightforward. And yes, it's kind of hard to see, but yes, I did have to put my logo on it because I have a logo. It needs to go on everything. Okay. So what that means is that I need to actually build a little bit something with this. So, hey, we're getting to the building part. So this time, the circuit is pretty straightforward. So using power supply going into the chip, which connects to a button, and that's pretty straightforward. The power supply has 2 sets of power outputs for 5 volt. You have your standard 5 volt in ground, and then you have standby 5 volt. Standby 5 volt is on all the time. So that's designed specifically to have all the processing to turn the system on with. We have the power on, which is just a ground connector. You just strap it to ground, power comes on. And power OK. Power OK is an interesting bit of circuit. It goes high at 5 volts when the power supply has completely settled. So what you want to do is to use this to trigger the reset circuitry, which is this blob down here, so that it doesn't you cannot disable the reset line on the CPU until the power supply has settled. Nice, simple safety feature, works really well. So, to build it, we don't really need to do much. So take that out, grab this. Now, first thing we want to do is actually make sure everything works. So, let's plug that in. Just a standard barrel jack, and I will turn the power on. All right, so power supply's on, power supply's off, and if I touch this to ground, power supply's on. Okay, so that's all working. So I only need a couple components for this. I need the logic, which is just really nice and simple. That plugs right there. And I need the switch itself, which goes right about there. Okay. So I have not practiced this ahead of time, so we're doing this live. Okay. All right, so we need a ground line that goes into 2 that needs to connect to 3 because the clear has to be pulled to ground. Because clear's active high, and clear is what clears it. It's designed to be the external clear of the... Yeah. It's what you use if you want to turn it off in software. So we'll connect ground and clear. We're going to need a connection of ground down to one leg of the switch. So that should do nicely. All right, that's connected, and we're going to need to have a slightly longer one to connect the output into the input line, which is pin 1. So that should work right there. Go in. All right, like that. That is just a little on the tight side. I might replace that with a slightly longer cable soon. All right. So that, and all the logic for pulling up the resistors and everything else is done in the chip. So I don't need to do anything other than that. And that should actually be it. So we take the ground line, we connect it to here. We take the standby power, we connect it to there, and we connect the power line to there. And we will connect both power rails. All right, there we are. So if everything worked and I didn't break anything, I should just be able to hit the button and it'll power on. All right, let's see how it goes. Hey, works like a champ. Powers on exactly when I want it to. So the last thing I need to do is to deal with power OK. Now the reset circuit over here is straightforward. It's a standard debounced button, so it gets pulled to high, and once the capacitor it's pulled to high, it goes to capacitor. Once the capacitor is charged, it will allow everything to work. Basically, until this capacitor is fully charged, it's going to be pulling the system down to reset. So what we want is to only charge up when I have the thing thinged. Oh, yes, I know how to speak. There we are. We want to only charge on when the power supply is okay. So when I do that, it's hard to notice, but it takes just a hair longer for it to turn on. But yeah, that's it. And of course, I can also just hit the physical switch, but the whole point is to have a soft button on this. But yeah, I will eventually hook up the ground into one of the bolts onto the breakout board. It's not going to be left floating around like that. I'm not that dumb. Sometimes I think I am, but I'm not. So yes, this is really the next thing I need. So this logic works, and between these two things, I will be able to build a board. Right now, I need 2 boards. I need a CPU board, basically replacement for this, that also contains all the various logic to latch the address lines, to route the data lines, and all that stuff. So that's a single board that does all the work for the CPU. And then I need a support board, which will add the power logic, the reset logic, breakout pins so I connect it to a breadboard for future designs. So those are the two boards I need to move this onto PCBs. So those are going to be being manufactured soon. I'll probably do a video reviewing the design of those, because they're almost but not quite the same as the logic that's on the breadboards. And once that's done, we'll be able to get it put onto the onto the PCBs. That's going to be fun because the CPU PCB is going to have something like 30 chips, and they're all surface mount because there wouldn't be room if they weren't. I will do a video going over the design of the new CPU board. For right now, though, this is where we're at. So, yeah. What's next now? Well, next, I'm not sure if I mentioned in previous videos, but I mentioned here that I have these IRQ lines on the data bus because I need interrupt handling. The UART works better with interrupt control. If I ever get any kind of video thing, interrupts are going to be necessary. So I need to integrate an interrupt controller into this system. Now, that's easy. That is a standard chip. You can buy them pretty cheap used nowadays. But where's the fun in that? So the next few actual build videos, hopefully starting in a couple weeks once I get all the parts, I am going to start building the interrupt controller from scratch using just discrete components. I got the logic mostly worked out. I don't think it's that bad. We'll see though. For now though, one last thing I want to add. While I am using this Nano ATX power connector, this is because I had one laying around. What I really probably be using is an ATX Mini, which has actual cooling, as opposed to being completely passive like this, because I'm not sure this is going to have enough cooling like this. But one of the benefits of using the ATX power connector is that ATX power supplies are not that expensive. They're easy to get, even secondhand, they're cheap. I mean, if I really want a cheap one, I can just go buy like a 10-year-old PC, pull it out, hey, standard power supply, works great. And this also provides 12 volts as well as 3.3 volts, and a very, very low amperage negative 12 volt line. So that's useful for other things. Not a lot of what works with modern computers needs 12 volts anymore. But if I wanted to do something with like a storage device, that might be necessary. Still, this is sort of the next logical step, and then we're going to start getting all this onto PCBs. And then the interrupt controller. So lots to go through. Oh, yes, and I still need to do stuff about the actual monitor code. I have been a little slow on that particular part of the system, mostly because I've just been a little slow on that. I just haven't had a chance to focus on it the way I would like to, so hopefully I'll be able to start doing that soon. Admittedly, part of the problem is that I promised to stream some of that work, and I get really camera shy, which is kind of funny because I'm doing these long YouTube videos, and I'm camera shy. I actually have to really psych myself up to do these recordings. So hopefully I can get through that and actually do some streaming soon on YouTube. Cross fingers. For now, though, there you are. That's the next couple steps and how things are going design-wise. So, for those of you who stuck around, I don't know how many would. I imagine this is a pretty dry video. Thank you for being here. Thank you for watching. I hope you found this entertaining, and I will see you next time.